Welcome to Mode Mind. Today, we are diving deep into the fascinating world of physics to explore a force that controls almost every single movement in our daily lives, yet often goes completely unnoticed: friction. From the microscopic ridges on a surface to the macro mechanics of heavy machinery, we are going to look at the inner workings of this incredible force, with a special emphasis on how rolling friction completely changes the game in engineering and modern transportation. Let's get started. To truly understand how this works, we first need to break down the definition and core types of friction. At its foundation, friction is the resistive force that opposes the relative motion between two surfaces in contact, and it primarily presents itself in two ways: static friction and kinetic friction. Think of static friction as the initial barrier. It is the force that firmly resists the very start of motion between two completely stationary surfaces. For instance, imagine trying to push a heavy wooden crate across a rough floor. That initial, stubborn resistance you feel before the crate even moves an inch is static friction working against you. Kinetic friction, on the other hand, takes over the exact moment the object actually starts moving. It is the continuous force opposing the movement of two surfaces sliding past each other once the motion has already started. Going back to our crate example, once you finally get it to budge and it starts sliding across the floor, it becomes noticeably easier to keep it moving than it was to get it started, and that is because kinetic friction is generally weaker than static friction. What actually creates this resistance in the first place? There are two primary factors affecting friction: surface roughness and normal force. If you look at any object under a powerful microscope, even a surface that feels perfectly smooth to your hand will look like a rugged mountain range full of microscopic peaks and valleys. When two surfaces come together, these microscopic irregularities interlock with one another, creating a physical barrier that increases friction and resists movement. The second major factor is the normal force, which is the perpendicular force pressing the two surfaces tightly together. Imagine pushing a light cardboard box across a table versus pushing that exact same box filled to the brim with heavy bricks. The heavier box exerts a massive downward normal force, pressing the microscopic peaks together much harder, which directly increases the magnitude of the frictional force and makes it significantly harder to push. These behaviors are governed by the fundamental laws of friction, which help engineers calculate exactly how materials will interact. The first law of friction states that the total frictional force is directly proportional to the normal force acting between the two surfaces in contact. This means if you double the weight pressing down on an object, you effectively double the friction you have to overcome to move it. Interestingly, the second law of friction states that the frictional force is entirely independent of the apparent contact area between the surfaces. Whether you try to slide a brick flat on its wide side or stand it up vertically on its narrow edge, the actual friction remains exactly the same because the total weight pressing down hasn't changed, proving that the surface area you see with the naked eye doesn't dictate the resistance. This brings us to one of the most revolutionary concepts in mechanical physics: rolling friction basics. There is a massive mechanical difference between trying to slide a heavy object versus rolling it. Sliding friction requires forcefully grinding the microscopic peaks of one surface directly against another, whereas rolling friction occurs when a perfectly round object rolls smoothly over a surface, resulting in a resistive force that is generally much less than sliding friction. The main causes of rolling friction stem from the subtle deformation of both the rolling object and the surface itself under the weight, along with very minor microscopic surface interactions causing resistance at the exact point of contact. Think about trying to drag a heavy couch across a carpeted floor. It requires an immense amount of effort due to intense sliding friction. But if you place that exact same couch onto small caster wheels, it glides across the room with a gentle push because rolling friction drastically minimizes the resistance. Friction is not just an abstract concept found in textbooks. It is absolutely vital to human survival and daily life. Consider the simple acts of walking and running. Every time your foot hits the ground, the intense friction between the soles of your shoes and the pavement prevents you from slipping backward, allowing for stable, controlled forward movement. If you have ever tried to walk across a sheet of perfectly smooth, wet ice, you know exactly how terrifying it is when that friction is suddenly removed. Similarly, friction is what allows for holding and gripping objects securely. The natural ridges on your hands interact with the surfaces of everyday items, helping you to firmly hold and manipulate everything from a heavy coffee mug to a slippery smartphone without them instantly dropping out of your hands. When it comes to friction in transportation, this force becomes the literal line between safety and disaster. The most direct example of this is found in modern vehicle braking systems. When you press down on a car's brake pedal, hydraulic pressure forces a rough brake pad to violently clamp down onto a spinning metal rotor. This intense friction instantly converts the vehicle's massive kinetic energy into heat energy, enabling the vehicle to safely slow down or come to a complete stop. To ensure the car stays glued to the road while this happens, advanced tire design and traction are crucial. The deep treads and specialized rubber compounds engineered into modern tires are specifically designed to maximize friction with the road surface, displacing water to maintain a powerful grip and giving the driver total steering control in dangerous, wet, or icy conditions. Looking at the broader scale of industrial applications, controlled friction is the primary mechanism used to keep the modern world moving. In mechanical engineering, friction is utilized for efficient power transmission through belt and chain drives. By wrapping a tight rubber belt or a heavy steel chain around rotating pulleys and shafts, the friction between the components allows rotational power to be transferred smoothly from a roaring motor to a machine without the belt slipping away. Beyond power transmission, controlled friction is actively harnessed in crucial manufacturing processes. Heavy industrial machining, precision grinding, and the intricate shaping of raw metals all rely heavily on calculated friction to cleanly cut, smooth down, and sculpt materials into the precise components required for high-tech manufacturing. Ultimately, understanding the role of rolling friction in machinery is the key to building an efficient, high-performing future. Inside almost every spinning machine on Earth, engineers utilize components like ball bearings and wheels to ensure that rolling friction minimizes resistance between rapidly moving parts, allowing for incredibly smooth and highly efficient rotation. By strategically converting harsh sliding friction into gentle rolling friction, industrial machines can radically reduce energy losses. Minimizing unnecessary friction inside mechanical engines and factory hardware helps conserve massive amounts of energy, minimizes destructive wear and tear, and significantly enhances the overall lifespan of vital mechanical components. Thank you so much for exploring the physics of friction with us today. If you found this deep dive insightful and want to keep expanding your mind with fascinating science and engineering content, please make sure to like this video, share it with your friends, and subscribe to Mode Mind for more. See you in the next one.